this video, we're going to talk about something called implicit differentiation. And so I think I'm just going to start by doing some examples and showing you how this works. In these problems, we're going to be taking derivatives and we're going to have both x's and y's. And the idea is that y is some function of x. We just don't know what that function is. So if I want to find the derivative of, say, y squared, I use my normal derivative rules. So the derivative of y squared would be 2y. But since y is actually a function of x, y is some other function, I have to multiply by whatever that derivative of y is. I'm going to call that y prime. This really is just a statement of the chain rule. And so the same idea would be true for the rest of these. Square root of y is the same thing as y to the 1/2. If I take the derivative of that, I would get a 1/2 y to the negative 1/2. But then using the chain rule, I have to multiply by whatever y prime is. If I wanted to rewrite this using a positive exponent, it would be 1 over 2 y to the 1/2 times y prime. Now, example C, x squared times y to the 3rd. In this case, we actually have a product, and so we'll use the product rule. I'm going to call my u x squared and the v y to the 3rd. So then my u prime would be 2x, and my v prime is 3y squared times y prime. Notice when we take derivatives of these y's, because they are functions of x, that's when we have to multiply by the y prime. So using the product rule, my derivative would be 2x times y to the 3rd plus 3y squared y prime times x squared. All right, let's do one more like this. X minus 3y to the 4th. This is going to be a chain rule problem. I have something to the 4th power, so the derivative is going to be 4 times that something to the 3rd power. And then the chain rule says I have to multiply by the derivative of what was inside. So I'm going to have to multiply by the derivative of x minus 3y, which would be 1 minus 3 times y prime. So I think the main idea here is our derivative rules are the same. The difference is if we're taking the derivative of a y, an output variable, we have to then multiply by a y prime, and that really is just the chain rule. Now the reason we're talking about implicit differentiation is because sometimes we have equations that aren't solved for y, and we want to find the derivative. So for example, if I want to find y prime, and I have the equation 2xy plus y squared equals x, and I don't want to actually solve for y, that's okay. We can take the derivative implicitly, just one term at a time. So I'm going to start with this 2xy. This is a product. I'll let my u equal 2x. My v is y. So u prime would be 2, and v prime is whatever y prime is. Using the product rule, I get 2 times y plus 2x times y prime. Now I'm going to find the derivative of the y squared. That should be 2y times y prime equals, and the derivative of x is just 1. So I took the derivative of each term in this equation, one term at a time. And now I'm going to try to solve for y prime. So I need everything with y prime on one side of the equation. Everything without y prime has to move to the other side. So I subtract the 2y. And now to solve for y prime, I'm actually going to factor a y prime out of the left-hand side. And that's going to allow me to get the y prime by itself. I can divide both sides by this 2x plus 2y. And that's it. I have solved for y prime. My y prime is 1 minus 2y over 2x plus 2y. All right, let's do another example that's similar. To find y prime, I'm going to take the derivative of one term at a time. So I'll start with the e to the y. The derivative of e to the y is e to the y. But then I have to multiply by y prime. The second term, y ln x, is a product. I'm going to let my u equal y, and my v is ln x. So u prime is y prime, and v prime is 1 over x. Using the product rule, I'm going to get u prime times v, so plus ln x times y prime plus v prime times u, so that's 1 over x times y. And then we've got an equals 5. 5 is a constant, and so the derivative of 5 is 0. Now to solve this thing for y prime, I want everything with y prime on one side of the equation, everything without y prime on the other side. So I'm going to subtract this y over x from both sides, and I get e to the y prime plus ln x y prime equals negative y over x. Now we can factor y prime out of the left-hand side. And then to solve for y prime, I am going to divide both sides by this e to the y plus ln x. If you're dividing and you have fractions, you can always multiply by the reciprocal. So that's going to give me y prime equals negative y over x times 1 over e to the y plus ln x, or negative y over x e to the y plus ln x. Finally, we can use this technique of implicit differentiation to write equations of tangent lines. Using the same ideas as before, the slope of the tangent line is the derivative. So I'm going to start by trying to find y prime. So I'm going to take the derivative of one term at a time. The derivative of x squared is 2x. The derivative of y squared would be 2y times y prime. And the derivative of 25 is 0. It's a constant. I can solve for y prime by subtracting the 2x. So 2y y prime equals negative 2x. And then we could divide both sides by 2y. So it looks like y prime is negative 2x over 2y. We could even reduce this to negative x over y. Now I want to find the equation of this tangent line at the point negative 3, 4. So when x is negative 3 and y is 4. And so to get the slope of my tangent line, I am going to plug the negative 3 in for x and the 4 in for y. That gives me a positive 3/4. And then finally, just like we did in the past, I am going to use that point slope formula, and I'm going to plug in the 3/4 for the slope, and I'll plug in my point for the x1, y1. So my final answer is going to be y minus 4, that's the y value, equals 3/4 times x minus negative 3, and I'll write that as y minus 4 equals 3/4 x plus 3. All right, and that's it. So I think one of the hardest parts about this section is don't forget about your product rule, your quotient rule, and your chain rule. That is going to pop up in some of these problems.